Today we're going to be talking about section 1.4, which is about matrix equations. In the last video, we talked about vector equations, which look like x1 times a vector plus x2 times another vector, and so on. But if we look at these variables, x1, x2 through xn, and think of them as a vector, we can actually write this in an even more concise manner. So we can take our vectors, a1 through an, and make those be the columns of a matrix, and then say we're multiplying that by the vector made of the variables x1 through xn. So we can take this vector equation that we had and write it as a matrix equation, A times X, where A is the matrix made up of the columns being the vectors that we had in our original vector equation. We can use this as a baseline definition for how to multiply a matrix by a vector. So let's take a look at this. Let's say we have a matrix here. This will be our A. And we have a vector that we'd like to multiply it by. This will be our X. We can multiply A times X by saying, okay, the 4 is our x1. Let's decompose this into our vector equation. So we'll have 4 times the first column of A, that is our A1. So 4 times 2, 8, minus 5, plus our x2, which is 7, times a2, which is the second column of A, so minus 3, 0, 2. And we can multiply this out component by component. So the top component will be 4 times 2 plus 7 times minus 3. The next component will be 4 times 8 plus 7 times 0, and the third component will just read across that third row is 4 times minus 5 plus 7 times 2. And if we do that out, what is that? 8 minus 21 is negative 13. 4 times 8 is 32. And 4 times minus 5 is negative 20, plus 14 is negative 6. So there we go. This is how we multiply a matrix times a vector. And we're getting that specifically from our vector equation that we talked about in the last video. We had a whole list of properties for vector equations and how those worked. And we have a similar thing, although much shorter, for matrix equations. Basically, our properties just tell us that matrices work in the same way as we hope. So if we have a matrix and we want to multiply it by vectors, we can add those two vectors together first and then multiply it, or we can multiply the matrix by each of those two vectors individually and then add them together. If we want to scale our vector, which is the other thing we can do with vectors, we can multiply it by its scalar multiple first and then multiply by the matrix, or multiply by the matrix and then scale it. So that's what we hope would happen. So this is how matrix equations work. So let's actually tie them to what we've been doing so far in term. So far in term, we started off the very first week with systems of linear equations, and we were able to put those systems of linear equations in augmented matrix form. So we would have a matrix, and each of these vectors, A1, A2, and so on, are columns of our matrix. And then this would be our solution vector B here. That was our augmented matrix that would encode a set of linear equations. In the last video, we talked about vector equations. So the vector equations would look like x1 a1 plus x2 a2 and so on. And if you have a vector equation, then you could set it equal to B, and we'd say B is a linear combination of A1 through AN. And today we just talked about matrix equations, and a matrix equation looks like AX equals B. These are all saying the exact same thing. So it seems like this week we've talked about new things, namely vector equations and matrix equations, but really those are just another way of thinking about systems of linear equations. So when we talk about a matrix equation having a solution, typically what we mean is we have an A and we have a B, and we want to know, does there exist a vector X that makes this work? So if a matrix equation has a solution, that's the same thing as saying, B is a linear combination of A1, A2 through AN, which is the same thing as saying our system of linear equations is consistent. So these all tell us the exact same thing. So again, our matrix equation is going to have a solution if and only if B is a linear combination of the columns of A. Just as a side note, let's make sure we're keeping track of sizes here. So if A is an M by N matrix, and let's remember what that means. M is the number of rows that A has, and N is the number of columns. So if A is an M by N matrix and AX equals B, let's say this has a solution, so we can actually write this down. Then what dimension is our vector X? How many elements will it have? Well, if we deconstruct our matrix equation into a vector equation, we see we'll need an X for every single A1, A2 through AN. So we'll need N X's. So X will live in Rn. What that means is there will be as many elements as X as there are columns in A. Okay. Now, what about B? Where does the vector B live? Well, AX equals B has a solution if and only if this augmented matrix has a solution, which means there should be as many things in B as there are rows in A. And there are M rows in A, so B should live in Rm. All right. So, another thing we might ask, we talked in the last video about span. So the span of a set of vectors is the set of vectors that can be made as a linear combination of those. So we might want to ask, all right, for what vectors B does this matrix equation have a solution? So another way of saying that is, what vectors B are linear combinations of each of those columns of A. So let's see how we might go about doing this. So we might ask ourselves, let's say our matrix A was 1, minus 3, minus 4, minus 3, 10, 12, 5, minus 15, minus 19. So here's our matrix A, and we might ask ourselves, okay, well, for what B would this have a solution? Well, what we can do is we can augment on our B, but we don't know what B is going to be. So we'll just go ahead and leave these as variables B1, B2, B3, and we'll figure out what values those could possibly have. And in order for B to be a solution, we would need our matrix to be consistent, right? That's what the matrix equation being the same thing as the system of linear equations is telling us. So we need this to be consistent. So what do? We try to get into reduced row echelon form and see where we can go from there. So if we want to get into reduced row echelon form, we already have a 1 in our first pivot position here. So we want to get zeros underneath. So we'll want to take row 2 and replace it with row 2 plus 3 copies of row 1 to get rid of this minus 3. And then row 3 we'll want to replace with row 3 minus 5 copies of row 1 to get rid of this 5 underneath. And when we do this, we want to carry our B's along with us. So this top row we're not doing anything with. This will end up looking the same. This will be B1. Our second row will be 3 times row 1. So 3 times 1 is 3, minus 3 is 0. 3 times minus 3 is minus 9, plus 10 is 1. 3 times minus 4 is minus 12, plus 12 is 0. And 3 times B1 plus B2 is 3B1 plus B2. Similarly, we've got minus 5 times 1 is minus 5, plus 5 is 0, 0 and 1. And minus 5 times B1 plus B3 is minus 5 times B1 plus B3. Great, so we're carrying along our variables, even though we don't know what these B1 through B3 are, we're carrying them along with us as we do our row operations. And we can keep doing this to get ourselves into reduced row echelon form. And if we keep on doing this, you will end up getting 1, 0, 0. And what do we get in our augmented side? This will simplify down to minus 10b1 plus 3b2 plus 4b3, and these ones will stay the same because we don't need to mess with those rows. They're already good. Okay, so what have we learned? Our question is, what values could we plug in to B1, B2, and B3 in order to get values for the x's, so in order for this to be consistent? And as we look at this, we realize it doesn't actually matter. We could plug in anything we want for B1, B2, and B3 because whatever we get out of this equation, for instance, would be our value for x3, right? There's nothing about the system that could make it inconsistent. What this means is for this particular matrix, anything can be a solution to AX equals B. Anything can be a linear combination of those columns of A, which means that the span of the columns of A is literally anything in R3. So this leads us to a theorem that ends up being kind of useful. So this theorem is the following are equivalent theorem, and I'll explain to you what I mean by that. So here's our theorem. We have a matrix, an m by n matrix, and we say the following are equivalent. So for every single b that lives in Rm, because that's where the b's live, Ax equals b has a solution. So it doesn't matter what we plug in for B1 all the way through Bn, no matter what, we're gonna have a solution. This is gonna be consistent. Another way of saying this is that every single B in Rm is a linear combination of the columns of A. Another way of saying this is if everything in Rm is a linear combination, then the columns span the entirety of Rm. And how did we see that made it work? A has a pivot position in every row. That means all of our variables can be defined. There's nothing about that system that would make it inconsistent. We say the following are equivalent. What that means is either every single one of these statements is true or every single one of them is false. So if A has a pivot position in every row, I know that all the rest of these are true without doing any extra work. Similarly, if A doesn't have a pivot position in every row, so if there's a row of all zeros, for instance, then I know that the columns of A won't span Rm. I'll have something a little bit smaller for my span. In class, I might abbreviate this to TFAE. So if you see that, that's what I mean. The following are equivalent. Either every single statement is true or every single statement is false. So that's all I have for you on matrix equations. Again, the main takeaway here is that everything that we've talked about so far is basically systems of linear equations in disguise. So if you're faced with a problem and you're not totally sure what to do with it, you probably can think of it as a linear system of linear equations. And what is the only tool we know how to do with systems of linear equations at this point? It's just putting it into a matrix and doing reduced row echelon form. So when in doubt, smack everything into a matrix and do reduced row echelon form. All right, I will see you in class.